Good morning, everyone. It's time to start. I'm going to do a short introduction, then we're going to jump right into it. Our moderator is still stuck in traffic somewhere, so she's coming quickly, but we can make a start without her, and she'll turn up just fine. Brief introductions. We've got Niels from Delphi, if you can briefly introduce yourself in 1 or 2 sentences.
Yes, Niels van der Geest from Delphi, Delphi Digital, specialist in data-driven growing.
Anja Dieleman from Noor.
The business unit Greenhouse Horticulture of Wageningen University and Research, and I'm a plant physiologist and working on some data science projects.
And I'm Paulo de Heer from TNO. I'm a data science consultant doing a lot of projects in the greenhouse as well. We have been doing projects together here in the same field, in the same vein, collaborating, seeing what we can do across this industry. And without further ado, we've got a few short presentations to introduce the projects, the things we've been doing, and then interactive panel discussion. So let's kick it off with Anja.
Okay, good morning all of you. Welcome in this session. It's an honor to have you here, and I'm happy that you have been able to get here so fast in large numbers. I would like to tell you something about a project that we are currently running. It's called Agros, towards an autonomous greenhouse. And why would we need autonomous greenhouses or data-driven cultivation? Well, very much it has to do with the increased complexity of production. If you look at the current company, you have an energy manager and a people's manager and a number of production managers and somebody who does the retail and the sales. So it's getting more and more complex, definitely due to increased energy prices, fluctuating product prices, and so on. So what we gradually see is a shift from small companies with a grower with green fingers to more complex production systems based on data and sensors. And of course, we're talking about autonomous cultivation. The term autonomous cultivation is already very polluted. That can range from an automatic control of a P-band in a climate computer to a system where you basically have a greenhouse that's completely run autonomously without any input of people. Well, in our project, we define autonomous cultivation as remote control of cultivation by intelligent algorithms. That's an important part, based on automated continuously collected information from crop, substrate, and climate sensors. So it's very much on data collection, and it's also very much on intelligent algorithms. And in this, it's not just climate control, but it's very much control of the production system. So the crop is central, and climate is just a means. So if you look at all those steps, we move from physiological knowledge to selecting the right sensors, to the use of climate and crop models and the intelligent algorithms to control. Well, I can talk for an hour on how we realized it, but I will jump, given the limited amount of time we have, to the final results. So we developed the knowledge, we developed or selected the sensors, and we developed the intelligent algorithms, and we gave a proof of principle. I would like to share some results of the proof of principle with you. We grew 3 cucumber crops in similar greenhouses, similar installation, similar everything. And control of these crops was based on, the first one was the reference, and that is a cultivation plan by a number of expert growers. The second one was a digital twin based on our crop and climate models. And the third one was a reinforcement learning algorithm that really was developed specifically for this project, that learned from scratch how to control a greenhouse. We run the crops from January until May, and we did data collection via cameras and sensors and validated those by manual measurements. And very important in any control that you can do in a greenhouse is the goal function. So we chose a goal function of net profit, in this case being the benefits from the cucumbers that were harvested and could be sold, And the costs were considered heat, electricity, and CO2. And I do realize that is a limited cost function, but definitely these are variable costs and benefits, so it works very well in the control. Well, looking back after a number of months, we had a very successful autonomous control. Our digital twin was able to control climate, irrigation, and the fruit pruning strategy completely autonomously during the entire cultivation. The reinforcement learning had learned only to control the climate yet. So irrigation and crop management was based on the grower strategy, but it learned and it was able to control climate by itself for the cultivation. Reference followed the cultivation plan, which you could also consider a model, but then a grower's model, with very little adjustments. And we had developed vision systems that were able to capture the data that we're looking for example, number of newly formed nodes. And this entire cultivation generated very valuable and complete data sets. Well, if you look at what happened in this proof of principle, then you see that we have costs of electricity, heating, and CO2 supply. The red line is the digital twin, which followed a very conservative strategy in terms of energy input. So it was definitely the lowest in costs of electricity and in total costs, since electricity were the majority of the costs. Whereas the reinforcement learning and the growers had more or less similar costs. If you look at went a bit too fast. If you look at the production, you see that the digital twin that was very conservative in energy input also had the lowest production. To the great relief of the growers were highest in production. And if you look at how that is feasible, you see that it was very much determined by the light use efficiency that all the cultivations had. So the light use efficiency, the number of kilos of product per mole of light, was approximately 20 for the digital twin, was higher for the reinforcement learning, but was highest for the growers. So basically, with the input of resources, the growers were able to produce most fruits. Well, if you look at the goal function, then you also see the funny thing is, of course, from the beginning onwards, the net profit is negative because you start with costs. You can see that the digital twin, with its conservative strategy, was least negative. And you can also see that from the moment that we started producing, so when there was income, that the lines were, well, very parallel. So for a very long time, strategies worked very nicely. I have to say that very much at the end, the growers did some very smart things in the final strategy, so ultimately they had the highest goal function. But what does this show? It shows that autonomous control of an entire production system, including, for example, crop management actions like fruit pruning strategy, is feasible. An advantage is that it can deal very well with uncertainties. Uncertainties in weather, in variable prices of inputs, for example, electricity, but also of product prices. And of course, it does face a number of challenges. You can imagine that the working of autonomous control very much depends on the reliability of data. So the input data has to be correct. Cybersecurity is a big thing. Suppose your company is hacked, then you definitely have a problem. Availability of internet, and currently we have proven the concept, but if you look at the adoption by growers, that is something that we will need to work in the coming period. So what are the next steps that we should be working on? Determine crop boundaries. So what is the validity domain of the control? Further developments in vision, because we want to have continuous input of data. Well, algorithms, but also very much grower involvement and application of the concept. Fortunately, we are capable of continuing this in the next Agros project. And of course, we cannot do this without a cooperation with a large number of companies with input of knowledge, resources, sensors, and whatever.
Yes. All right. Switching over to our second presentation, which will be shared between Niels and me. I'll present something on the CODED project, Coupling Digital Twins. It's an acronym for. And it's a project where Delphi, Wur, and TNO have collaborated in pushing these digital twins a step further. No longer have we only one digital twin, but we have multiple digital twins spread over these different parties that we connect together and connect to the greenhouse and see what kind of improvements we get from that. Let's see if it works. Yes, it works. Okay. So at TNO, we're not just a company. We do applied research. We bring various other groups together, and with this way, we orchestrate this innovation. And we provide norms. It's not really responding, it seems.
Hey guys, it's not responding.
Why do we have to aim it? There we go. Okay, so yeah, you hear a lot about AI and sensors and models and this data ecosystem, but where are we actually on this roadmap? Improvements have been made in computer vision, indoor climate, greenhouse systems. But if you look at the hype cycle of autonomous growing, a lot of companies are popping up. We see it here everywhere, but it feels kind of like we're still here in the bottom right. We can do a lot, but when it comes to the real world, a lot of stuff is still tricky. Anja showed some really great stuff on how to really get there with these newest technologies. But what are these gaps and these challenges? Data, Anja mentioned it as well. Proper simulators to train in these models in a better way without having to wait many crop cycles. And I would say also this holistic connectivity between these models, between these systems. Growers look at it only from the plant. The turnkey builders look at it from the systems that they provide. But actually you need to connect everything because everything is getting so automated, but you cannot look at your irrigation, at your lighting, at your plants individually. Everything needs to be connected in order to optimally control and also know what's going to happen in the future in terms of outdoor climates. So that's where this digital twin comes in. What is a digital twin? Anja mentioned it, that they used it, but what actually is it? It's a live model that is fed with continuous data from its physical counterpart. And it's a perfect replica in a digital world of this physical counterpart. Can mean different things, but you can use it for a lot of things as well. You can use it for steering the greenhouse, simulating what could happen in a different scenario, in a different use case, predictive maintenance as well. And digital twinning is really one of our key technologies at TNO that we also push in various sectors, for bridges, for built environment, also in greenhouses. And how does that look? What can we do with this? Well, if we couple these greenhouses, couple these digital twins, we can get a much better prediction of what the crop is gonna do when we turn the lights in a different way, when we tune the humidity or the CO2 dosing in a different way. And with this, you can create new business models for both the manufacturers of the systems, the growers, and also the seed developers. And with this project, our goal is really to create a blueprint for other companies on how they can couple digital twins in the greenhouse. What are our lessons learned? What should you be doing? What should you not be doing? And how to do it. So those will be our results. And we're not doing that alone. We're doing that in a deep collaboration with Delphi and Wageningen, using their knowledge, and some other companies in the Hortivation Foundation, as well as for the actual crop trials that we're running. A lot of companies, sensor companies, are involved in developing these new sensors, processing the data, and how we can connect them up as well. So what does it look like practically? Well, from TNO, we have the Sion model, it's a way to simulate the greenhouse with all the systems that are in it. So you model everything from the size of the greenhouse, every system that is placed where, what they're doing, and you can. It has integrated plant models, and with that you can run full year crops in a fictional greenhouse anywhere in the world. So you can, if you're trying to build a new greenhouse, you can kind of build a virtual one before you have to do it for real, and then you can know how well it would do in certain cases, warmer years, cooler years, etc. It has internal plant models, but for this project, we connected it to the Wageningen's Income plant model for tomato crop.
Then I'll give it to you in time.
And lastly, there's the QMS model from Delphi. Niels will talk a bit more about that. It's the quality management system. And that's where the grower inputs their overall strategy for the year on how they want to manage their crop, when to cut leaves, when to harvest, how big the trusses should be, and also a primary goal for the indoor climate settings on a global scale over the weeks. We connect those together. They're all turned into digital twins, so we're connecting them to the physical twin as well. And then we're connecting those together to simulate in tandem, together with each other, every step, exchange this data. What would happen if? What would happen if? And with that, we get this data from the physical twin, from the sensors and the growth results, and out of this comes a growing strategy that's directly fed into the Prefab Climate Computer to control the physical twin in the greenhouse. And how do we get to a strategy? For that, we added an optimizer, and that's also an external system, so they're all hooked together through APIs in kind of standardized fashion. The goal is to do this through the Hortivation Hub as a central data sharing platform. It's really the protocols to share the data and not somewhere something where you store the data. And with this way, in this way, we can have the more accurate system modeling from Sion with the more accurate plant modeling from Income and the more accurate grower desires and plans from QMS. Well, how does it look technically? I won't go into too much detail. A lot of technological developments have been made. I will highlight 4 points. We have the common greenhouse ontology, which is a way to define how things are measured and what they measure in greenhouses, all in a relational way, so you know how things relate to each other. This sensor is placed there, connected to this beam, and it measures this in those units, and that's saying something about the plants in X, Y, Z way. And that's all formulated. So then you can have all these systems in a more rule-based manner control this. You see here some relations to each other. For example, you have the heating pipe that's part of the heating system, and it's connected to the central heating. We have this digital twin blueprint, already mentioned it, for creating the knowledge and the rules for how to do this connectivity and best practices to share with the world. We create these connections between the digital twins. And lastly, we implemented an external optimizer. And for this, we used an evolutionary algorithm. That's another flavor of optimizing, kind of similar to a reinforcement learning algorithm, which Anja mentioned just now, but slightly different in the sense that we generate full solutions, a large population of them. We try them out in these simulations with Sion, Income, simulate them, run them, and do that many times, every time evolving, combining in a different way. And then at the end, we get a strategy that should work between the boundaries that we set it. At the end, we get many multiple optimal solutions that are each optimal in a different way. And from this set, this Pareto set, we, or the growth advisor, or the grower, can choose one that kind of best fits their needs. Because this is a multi-objective problem, right? We're trying to minimize cost, increasing profit. The cost has different factors in it, from CO2 dosing, energy, and gas for heating. So you want to all combine those in one fashion. And for this, a multi-objective evolutionary algorithm is a really good approach. And this is the dashboard that brings it all together, the front-end dashboard for the grower, where through multiple tabs you can select what you need, what you want as settings, start the simulations, can run overnight, can run live if you want it, and then you will get some results in here. And you can make the comparison to the actual greenhouse results over the previous weeks, how they've been growing, comparing what the digital twins, connected digital twins, have been proposing to do, and what they have been thinking that the greenhouse should be producing in results, and what has actually been resulted in the trials. So for these trials, they were run at the Delphi Improvement Center. Here are some images. It's quite a challenge because with this strategy we chose for a cold growing, energy efficient growing, so a bit colder in the colder months of the year as well. Was a challenge with humidity, botrytis, low temperature, and we have technical challenges as well in terms of data availability. Anja mentioned it as an example as well. But overall, well, while it's difficult, we're still going with the crop. It's still going nicely, and I think Niels can take it over from here.
Yes, thank you very much for the presentation, Paolo. Paolo presented already the overview of this project. I will go deeper into how the QMS tool is used within this project. So yeah, QMS, Paolo already mentioned, stands for Quality Management System, and this is specifically for the tomato crop, this tool. To emphasize, this tool is like a cultivar-specific tool. We have different kinds of segments: trust tomatoes, beef tomatoes, cherry tomatoes, and within every segment, a lot of different varieties. So for every variety that we are modeling, we use a specific cultivar profile. And here we see some parameters which are set in that cultivar profile that we use for our modeling and calculations. So if we move on, the QMS tomato tool is used as a start to create a strategy to feed the models, to feed data to the models for the digital twin. And before we start this project, we set some goals for the cultivation. So the goals for fruit weight, what are the amount of fruits per toss that we want to have, and which is also feasible to have. What kind of prediction do we want to realize, and what kind of resources do we want to use, which are available. But to reach these goals, it's also important to have a plan which is feasible and also realistic. So what kind of temperatures in, let's say 24-hour temperatures do I want to realize? What kind of radiation levels can I expect based from outside, but also from my lighting system? Which kind of cultivar I'm going to use? The cultivar is important to use that cultivar profile. And also the stem density. What is the start stem density? When to increase, when to decrease. All those parameters are important to create a cultivation strategy which is feasible and but also realistic. So that we did for this project. So I want to explain you a bit how a user can use this tool and how we implement this tool for this project. So if you're a user and you want to create a strategy before you're going to plant, you can use this tool to simulate different scenarios, let's say scenario A, B, and C, with all different kinds of strategies. In case of pruning strategy, maybe a different cultivar, maybe increasing lighting hours, and then you can easily compare your strategy and also the resources that you want to use within your strategy. So these are some examples that you can implement, and based on these, you can select which one is the most realistic and also feasible to implement in your cultivation, and then you're going to use that scenario to follow up during your cultivation. When the user selected the scenario, he's going to follow his scenario by, we call it an adaptive strategy. So every week he's going to, you're going to fill the model with realized data. So for one side, from the climate, so what was the realized climate? And on the other side, what was my realized crop development? Let's say flowering speed, setting speed, but also when you have harvest, what was my fruit weight? What was the ripening time of my fruit? So in this way, you are following your cultivation, and within this project, every week from this model, we are feeding again the digital twins. So there's data which is going from the QMS tool into the SEOM and income models. And after the cultivation, well, the project is still running, but after the cultivation, we will do also an analysis. Okay, how was the cultivar performing? We do a cultivar analysis, and we can also, based on that, we update the cultivar profile specifically for this project. So this is briefly how the user can use this program to create strategies for this cultivation. So when looking to the future of the data-driven growing perspective, by using tools like this, you can create insights for the user, let's say the grower, to have more insight into the cultivation. You can already create scenarios and strategies before you're going to plant, before you can see the plants already. You can follow up your cultivation. You can also change your strategy during the year. And you have a more accurate prediction, for example, for your yield. And it gives also the possibility to adjust, if necessary, during the year, your strategy, so you have a more optimal result of the overall cultivation. So, that was in briefly how QMS tool is implemented in the overall project. And that was the end of our presentations. I think we haven't seen our moderator yet, so I think we will moderate by ourselves.
Is she here, Tiffany, or hasn't she arrived yet? No, okay,
No.
she hasn't arrived yet. All right. Thanks. If you sit there, you're the moderator, dude, so feel free.
So, first of all, are there any questions from the audience? Yes.
If they have any questions, could you? Well,
So, is
So
there's a
maybe
microphone coming.
Yes, I can repeat already. So the question was why the digital twin was the worst performing from the three. Do you want to answer?
Yeah, first of all, I definitely do not agree with the term worst performing.
I was provocative on purpose.
Yeah, no, that's fine, that's fine, that's fine. I did show you the results in terms of the results of the net profit. Technically, I think this was one of the first times that ever, under completely the same conditions, and let's say a grower's cultivation and a digital twin and a reinforcement learning was compared. So I have always considered it a learning experience rather than a competition. And now to answer your question, there are always strategies to pick. And if you look at the goal function, which was costs and benefits, strategy of the digital twin was very deliberately to cut on the costs, which resulted in a specific crop. And you may also say, okay, perhaps not all crop knowledge was completely implemented in the model. And if the model is not completely up to date, your control is not completely up to date. Whereas the growers, and this is a bit, again, provocative to say, the growers said, we don't care about the cost. We are going to grow the best crop that we can, and in the end, we will see what happened. Well, that proved to be a strategy that worked very well. So what we did is we learned from whatever we saw there, and I would never express it as that one was worse than the other. I mean, it was definitely, the digital twin was capable of controlling, let's say, everything. So crop management activities. Every Monday, our greenhouse staff got a leaflet from the control saying this many, you have to prune this many fruits in the coming week. It controlled irrigation, it controlled climate for 4 months completely independently. Whereas, for example, the reinforcement learning had not learned the crop yet, so had to rely on the grower's knowledge and expertise for a number of crop management activities. So also in that sense, comparison was not fair.
Follow-up. The reinforcement learning, do you feel that you had trained it as much as you would like? If it had more training
No.
data, would it have?
The reinforcement learning was trained to the extent that we had the time available. And definitely, if you look at a cucumber crop, it starts with initial phase until it is in full production. Then it's a production phase, and then it's a phase where it's decapitated and you do a final run. Well, it learned the middle part, more or less, but it did not really learn the crop yet. So in the next project, we will work on the learning bit of the crop. So it was only capable of doing climate yet, which was already an achievement, but definitely not a full control. Any other questions?
Really, no questions.
Well, then I have a question
Yeah.
for the two of you, especially for Niels. What will be the future of, let's say, data-driven cultivation? What are the first steps that we need to take?
I think the most important step to take is that we are working all together with the same data. That we are collecting the right data with the right methods, using the same standards, that we are all calculating and modeling with the same data. But because when you want to model, your input for the model, it's important to have also accurate and good outputs. So we're already innovating there, but there's still a big step to go. So that we all looking to the same things, and we also can work all together with the same data to benefit from each other there. So I think that's the first challenge to move on. But I'm also curious what you think about this.
Yeah, I mostly agree with your statement, Niels. Co- Getting this data to a more mature level and being able to connect them together in the models, super important. One other thing I was thinking of as well, and we encountered that with the growth trials at the Improvement Center of Delphi now, is trust and letting go of control in this way. And that's also super tricky because it's either 100 or 0 to let go of control this way, right? If you have this autonomous system. And building that trust is really difficult. So I think what's really important is to, in the development phase of these systems, of these autonomous systems and these models, to incorporate the explainability, the understanding, and the way that the grower needs to know that it can fully depend on this. And you won't be able, I think, to do that to 100% at the start. You really need to also make ways for your systems and your greenhouse to control it, maybe like starting 25% autonomously, 50% autonomously. And I think that's a really interesting challenge to think of how will a greenhouse look, what will a greenhouse look like, and the operation with 50% control and more than that, and in a way that it can slowly ramp up. Not that you're locked in, that you say, oh, we have our climate computer and it's doing some weather predictions from outside and some autonomous opening and closing. No, but really in a way that you can have it in a gradual fashion to slowly ramp up this autonomy as your trust goes up. Do you have thoughts about that, Anja?
Yeah, I'm a bit struggled by the word 50% control. What does make sense is you can control a number of things. You can control irrigation, you can control climate, you can control the crop strategy. So it does make sense to start, for example, with irrigation control, because that is something that is already commonly done by a climate computer. And next one is climate control, where you say these are the boundaries of the system, but the system is allowed to determine a heating strategy, a lighting strategy, a window opening strategy, for example, taking energy costs into account, and then gradually move to the the crop management activities. In that way, it's more. It's easier for a grower to oversee the different bits, and if you have trust in irrigation control, it makes sense that you can have trust in a climate control, and then it makes sense that you have trust in the next step. But I'm a bit struggled with 50% control.
So that was just a number, right? But it's about giving this gradual increase. I think that's super important as a way to build this trust, and as a way to build this trust. I think that's another point, maybe in favor of digital twins compared to, for example, reinforcement learning, where reinforcement learning is my background, so I'm bashing my own child here. It's not like I'm biased, but reinforcement learning at its core it remains a very black box kind of system. It's very difficult to get explainability out of a reinforcement learning system, and I think with a digital twin, where you have everything really properly modeled of what's going on in the greenhouse, you allow for much more explainability and also control in that way, maybe to this grower or advisor or user, in what are these systems doing, why is this coming out of here, and maybe how can I still change this direction. So that's maybe also what I'm saying about 50% control. It's not just about fully managing some aspects and not fully managing some others, but your level of management may be also being at some intermediate stage. on purpose?
There's a question
Oh.
over there.
Also there. So can the microphone go that way?
Where was the question?
There.
Oh yeah, in the back there. Yeah.
My question is, what were the risks during your experiments, and what were the key situations that affected different strategies? What were the important risks that affected the AI strategy, the digital twin strategy, compared to the raw risk?
Well, so the question is, what were the risks during our cultivation? Well, a very simple one is that we lost, for whichever reason, internet connection for 1.5 days. Well, then you're definitely in trouble because your control is not sent to the climate computer. So one of the things that you always need to have is a backup control. So suppose that you cannot control anymore, then this is your fallback scenario in terms of climate conditions. So that is one very simple, obvious thing. In terms of control, we had algorithms in place which functioned well. But an important one is the quality of input data. And we have been working on camera vision, for example, to determine the number of newly formed leaves. And in cucumber, that's very important because technically every leaf has a cucumber, which will be the harvestable product in 2 weeks. But quality of the input data is very important. For example, suppose I control irrigation. I do that based on the drain data, but one of the tubes went loose and the data are incorrect, then my irrigation strategy is incorrect. So in our trial, in our proof of concept, we based everything on manual data, but definitely a next step is to do that on sensor data, vision, whatever. But in my understanding, we always need a double. So if you have, for example, drain data, I would prefer to have a model running, calculating the expected drain. If the two more or less match, then you have valid data. If one is really off, that implies that you have to go into the greenhouse and check, because the model might also be off. So I did not dare to take the risk, but if I would have done that, I might have run into problems with my input data.
Yeah.
Yeah, and one of the things, fortunately, it did not happen, but it may happen, is cybersecurity. If you get hacked as a company, you're in trouble. But I mean, that is something that is also now, it would be the case. Also now, if a commercial company would be hacked, you have a problem.
Yeah. For our case, just to add to that, input data quality, super important, and also something we struggled with. During the runtime that we discovered that cases were just a bit different, or the data collected by the QMS system, for example, had changed a bit, meaning that the other systems had to adapt to that as well, or cope with that at least. So that's from the cybersecurity aspect, and not just in terms of attacks, but just in robustness of your software systems. Becomes more of a challenge with the approach that we had here with all of these different systems that have these APIs that are connecting with. They're running on various servers. Oh, this time this server fell down or broke down, and another time something else broke down, and we have to kind of look what caused this and how do we get it back up and running, and how do we prevent that in the future. So that's also knowledge, experiences, that's becoming part of our blueprint for digital twin connectivity. How do you do this in a way that it's robust, that they can keep connecting with each other, that they have fallback data to fall back on, and maybe in terms of risks.
Yeah, another risk are like maybe plant diseases. We discovered like during the trial, at a certain moment we had botrytis in the compartments. So that's also, you need to analyze the plant, how it's going, how is it developing, and also in that moment we need to interact with the models to adjust it and to save the plants. Otherwise, when you don't do that, so there's always that interaction needed when analyzing the plants to avoid risk like this. So that's also an important aspect.
Yeah.
There's a question over there. Just before you.
Just
So you've been running trials. How far do you think we are implementing digital twins partially or fully at transforming our businesses to fully?
In commercial horticulture, you mean? Yeah, that is a very good question. If you look at what is, there are, fortunately, there are a number of companies that are already working on implementing, let's say, data-driven horticulture. I think that would be the best description. And a number of them have taken it to the level that Niels was already mentioning. Quality of data, even if you're working on manually collected plant data, if you ask 5 people to do it, you get 5 different data sets. So that is a very important one. That's the first step. And what you see is, fortunately, that the mindset of horticulture has changed compared to 5 years ago. Then Dutch growers at least said, oh yeah, but we can do better than any control. It would be interesting abroad for where they don't know how to cultivate. That has changed. So as far as I know, there are no companies really controlled autonomously. But I think if you would be looking in 5 years, that would be completely different. And it would indeed, as Paulo already mentioned, I think it's easiest if you take, let's say, the digital twin approach, that you have a mechanistic model so that you can understand what you do. And gradually, stepwise, that should be implemented. But I think there is still a lot to do in the coming, let's say, 5 years. And fortunately, you see from all different angles, sensors, data platforms, companies implementing, that it's, I think we're really going very fast now.
Yeah. I see another question there.
And since we have only 1.5 minutes, this is going to be the last question of the session.
How was the data collected? What was the basic infrastructure that you used, and how much was it manual? Did you have to, for example, collect the leaf area index manually, or what was the sensors you used?
Niels?
Yes, well, the plant measurements is all manual, but also, like Paolo mentioned in his presentation, a lot of like also plant sensors and climate sensors were involved, which are like running also in the background of this project. So climate was mainly by sensors, like everywhere, also some plant sensors, but mostly of the plant was done manually. So yeah, to answer your question.
Okay, yeah, perhaps you should do it as the chairman, but given time, I think we are going to close this session. And we would like to thank all of you very much for your presence here.
Thank you so much.
Thank you.
Later in the afternoon, at the Meet the Expert stage right here, you can meet Niels. You will be
yes, at 3 o'clock.
there. Yeah, at 3 o'clock. And the rest of us will be at our stands, Wageningen and TNO, just over there in the hall as well. So you can look us up and have a further chat. Looking forward to it. Thank you.
Enjoy the day.
Gelijk af.
Hello. No problem.
Hey. Hey. Yeah, yeah,
Yeah.
That's the best way of management, like just delegating. Well done, well done.
It was all in the preparation.
You did have a very good preparation, so that did help us now as well. Yeah.